SwayamPrabha. Digital India. Educated India.
Okay, welcome back, and we are in the middle of the discussion of this coupling of kinetics and the thermodynamics, and we started with some simple example, and the one that we are discussing is the constant pressure fixed mass reactor, and there will be few more that we will take it up and look at this application. So, this is where we are actually looking at it. This is a constant pressure fixed mass reactor, that was the schematic, just to give you a quick refreshment where we stopped, and these are the assumption. Then we wrote our energy equation, and then we got the enthalpy, and then we have work. This is one of the biggest assumption, that work is only the P dV work. Then finally, we replace that thing, and this is where we stopped it, the ideal gas behavior. Now, this is equation 5.7. Now, the 5.7 provide the link to the system temperature, and the system composition they are linked with like this. So, this is 5.8, and now chemical dynamics, that can be linked with the like B W dot I. So, that is my where omega dot I is the net production of species I. So, this already we have seen it. Now, once we substitute this 5.7 into 5.8 in 9. So, basically we want to substitute 5.7 to 5.9 into 5.6. Once you do that, what we get is that dt by dt is q dot by v minus some I h I w dot or omega dot I, and which is a sum over xi Cpi bar. So, this will take over all the species there. Now, once we use the calorific equation of state, which states that this is h I bar is h naught f I plus T reference to T Cpi dt. So, that what we get. Now, one can find out using this the volume. So, that can be easily obtained, and the volume would be m by I xi concentration molecular weight of I, which is now this is the change with time, this is change with time as a result of both chemical reaction and changing volume. So, what one can write that d xi by T is d B by dt, which is 1 by volume dNi by dt minus Ni 1 by volume square dV by dt. So, or one can write dxi by dt omega dot I minus 1 by v dV by dt. That is my 13b. So, again we use the ideal gas law, which is nothing but PV summation over I Ni RUT. Now, here P is constant. So, if you differentiate this equation and rearrange that, this will get 1 by V dV by dt 1 by summation over I Ni summation over I dNi by dt plus 1 by T dt by dt. So, for this particular system pressure is constant. Now, we substitute 5.9 into 5.14 B and then we substitute the result of 5.13 B. So, that will get us the change of concentration omega dot I minus xi, which is summation omega dot I summation j xj plus 1 by T dt by dt. So, in summary, the problem is to find out the solution of the following two set of differential equation. One is that dt by T equals to function of this and T, that is number 1, and the second one would be this is a function of and T for I equals to 1 to 2n. So, this is the bottom line two set of equation and the whole idea is to find out the solution of these two. So, these equations are subjected to some initial conditions where T at 0 is T naught and concentration at T 0 equals to x I naught. So, this is A and this is B. Now, this functional form of these two equations are obtained from equation 5.10 and 15 and 5.11 gives you enthalpy and equation 5.12 gives volume. But what happens most of the time there is no analytical solution. So, one has to go by some numerical technique like numerical integration and which somehow is capable of handling this steep system. Now, we will move to the next reactor, which is a constant volume fixed mass reactor. So, this volume is fixed and things should only change with time. Now, again this case also energy equation will apply, which will be similar to constant pressure case, and only exception here is that this particular case. So, this case our W dot is 0 for V constant. Previously, since V was changing, so there is a work done due to PdV work. So, my energy equation will get me du by dt is q dot by m. Now, U here plays the same role as H in our analysis for P constant. Now, the equations or that we got from 5.5 to 5.7. So, similar things can be developed here and can be used in this particular equation. So, whatever essentially 5. So, this is one expression this is second expression, this is the third expression. So, all these would be applicable and we can use them up and put it in this particular equation to get that my dt by dt would be q dot by v minus summation ui w dot I divided by CVI. So, that is my temperature. Now, you have ui equals to hi minus RUT and CVI is CPI minus RU. So, once we put them back, we get dt by dt equals to q dot by v plus summation of I omega dot I minus hi by summation I this CPI minus RU. So, this is what we get, and here dP by dt is quite important. This is important for this V equals to constant case, because P constant case that term disappeared. So, in this case this will not disappear and that would be quite important. Now, to get dP by dt again we will start using the ideal gas law, which is PV equals to summation over I Ni RUT, and we get dP by dt RT d summation over I by dt and P is all the species RUT. So, that is the total pressure of the system. So, from here we get V dP by dt RUT omega dot I plus RU summation I xi dt by dt. Now, this 5.20 can be integrated and simultaneously with Wt to determine T and AT. So, what we get dt by dt is a function of this and this we get a function of this and T for I equals to 1, 2 such that n. So, these are my. Now, this set of equation they can be solved with the initial conditions like T 0 equals to T naught and xi T 0 equals to naught. So, these are the initial conditions. So, this set of equation can be solved subjected to this initial condition. Now, that is how you get the solution for the temperature and the concentration in the volume constant reactor. Now, we will go to the well stirred reactor. So, the well stirred reactor is essentially the perfectly stirred reactor. It is a ideal reactor with perfect mixing achieved inside the control volume. So, this is quite often used experimental setup for flame stability. One has to, if someone wants to measure pollutant, then global reaction parameter, long well reactor, Zeldovich reactor, these are some of the applications. Now, this is the picture of that or the well starred reactor, where the inlet species they are coming in, there is a going out, this is a control volume, and things are well mixed inside that. So, again the mass conservation for any arbitrary species, that one can write by dt equals to m dot I v plus m dot I in, m dot I out. So, this rate at which the mass of I is generated, this is mass of the flow of I which comes into the control volume, this is what goes out of the, and this is the rate at which this changes. So, that is you get the. Now, m dot I v, this is the source term. So, essentially this is either generation or destruction of species by chemical reaction through transformation of one species to another species. Now, also we can write that d mCb by dt equals to m dot in minus m dot out, and when we related this with the reaction rate, so this is molecular weight and we can write that. Now, ignoring the diffusion flux, one can write that m dot I equals to m dot y I. So, this is by ignoring the diffusion flux. Now, one can apply equation 5.27 to well starred reactor, and the time derivative on left hand side disappears for steady state. So, this is one can use that. So, with now combining this equation, combining 5.29, 5.30 and 5.27. So, one can write that omega dot molecular weight of I v plus m dot y I in minus y I out equals to 0, I equals to 1 to n. So, further y I out is y I of the control volume, and species production rate omega dot I is a function of, this is at the constant volume and temperature, which is also a function of constant volume out, and this is in and that is out, where one y I one can get x I molecular weight I divided by summation of j 1 to n x j j. So, this what one can get it out. Now, 5.31 here, this can be written for n number of species to provide n number of equation, because this equation is valid for 1 to n and there would be n plus 1 unknown, assuming m dot and v are known. So, the additional equation comes from the energy balance. Now, what we can write, that steady state, steady flow, energy conservation for well starred reactor, where we get q dot equals to m dot h out minus h in, which neglect any changes in kinetic and potential energy. Now, in terms of individual species, so this neglect kinetic energy and potential energy. So, now in terms of individual species, this equation 5.34 becomes q dot equals to m dot summation I equals to 1 to n, where out h I t minus I equals to 1 to n H I at T inlet. So, where H I T is enthalpy of formation plus C P I d T. So, finding T and Y in Y I out is similar to equilibrium frame T calculation, but the composition is constant by kinetics. So, now most of the time mean residence time is defined for well started reactor, and that is T R equals to rho V by m dot. So, this is mean residence time. Now, where the mixture density is rho equals to P molecular weight of the mixture by R T. So, the equations which described in the well started reactor are a set of nonlinear algebraic equations rather than a system of. So, the equation system are non-linear algebraic equations rather than system of an ordinary differential equation. Now, we go to the last reactor, which is a plug flow reactor. So, the plug flow reactor is like that, where is the mass coming in, going out, and they are the steady state steady flow, but no axial mixing. So, the assumptions lies here at the steady state steady flow, no mixing in the axial direction, molecular and turbulent mass diffusion in flow direction is also negligible, uniform properties in the direction perpendicular to the flow, that means it essentially talks about one dimensional flow, ideal frictionless flow. So, pressure velocity can be related by Euler equation and it follows ideal gas behavior. So, that is the schematic of the system. So, now we basically write down for mass conservation. So, that is the control volume. If you check, whatever comes in, it goes, basically this is x and this is x plus delta x. So, that strip is for small infinitesimal element of delta x width. So, that is a mass conservation, then there will be momentum conservation, and then there will be energy conservation, this much of energy coming in, this is going out, and if there is a heat transfer takes place, and finally species conservation comes in, goes out, and some generation or destruction. So, these are the four governing equations one required. One is the mass, momentum, energy, species mass transfer equation. So, what is the idea? Idea is to develop a system of first order ODEs whose solution describes the reactor flow properties as a function of axial distance. Total we have 6 plus 2n equation, an unknown or function. So, the number of unknowns can be reduced by n, noting that w dot I can be expressed in terms of y I. So, the known quantities are mass m dot, k I, a x, q dot. So, this one can calculate from the given wall temperature distribution. Okay. Now, these are the fundamental conservation: mass, x momentum, energy, species. So, the number of equations are 3 plus n, and the variables or derivative involved are d rho by dx, bx, px, dh, yi. This is for number of species, and omega dot I. Mass action law or mass conservation n, which is omega dot I. The variables: equation of state 1, which contains these derivatives, d rho by dx, dp by dx, dt by dx, and this calorific equation of state and the definition of mixture molecular weight. So, these are the source of equation, number of equations, and the variables which are involved. Now, mass conservation, you get ddx of rho Vx A equals to 0, that is your 5.39. Then x momentum equation, you get dp by dx plus rho Vx dv by x equals to 0, and then energy you get d h plus Vx square by 2 dx plus q dot p by m dot equals to 0. So, Vx is the axial velocity, p is the local parameter, and species conservation dy by dx minus omega dot I molecular weight by rho Vx equals to 0. So, now equation 5.39 to 5.41 one can rearrange and get that 1 by rho d rho by dx plus 1 by Vx d Vx by x 1 by dx dA by dx equals to 0, and one write dH by dx plus Vx plus that local parameter by m dot equals to 0. So, using the ideal calorific equation where H is a function of temperature and the mass fraction. So, dH by dx can be related with Cp dt by dx plus summation y to n hi dyi by dx. So, this is 5.46. To complete the mathematical description, one more require is that ideal gas law, which is this. So, these are the set of equation, and so one will get 1 by rho dp by dx equals to 1 by rho d rho by dx plus 1 by t dt by dx 1 by molecular weight mixing d mix by dx, where mw mixing equals to nothing but summation of I 1 to n yi by mwi inverse, and dmw mix by dx equals to minus mw mix square 1 by mwi dyi by dx, which is now number of equations which are here are basically can be reduced by eliminating some of the derivative by substitution, and one can find out the d rho by dx equals to a plus b p plus 1 plus Vx square by Cpt minus rho Vx square. So, this is what you get, where A equals to 1 minus Ru Cp molecular weight mixing rho square Vx square 1 by A dA by dx, B equals to rho Ru Vx Cp m W mix 1 to n m Wi omega dot I hi minus mw mix mwi Cpt. So, this is what you get, and we will stop here and finish the rest of the derivation in the follow up lecture. Thank you.